My name is Alexander Grishin, and I'm a PhD student at High School of Economics. And today I'm going to firstly briefly remind you as the basic concept of Q-learning, and then I will introduce you the concept of distributional perspective on the reinforcement learning. And please feel free to interrupt me and ask questions in any moment. At first, we will discuss the important concepts of Q-learning. Then I will introduce you the distributional perspective. Then we will discuss importance convergence properties of these algorithms. And at the end, I will introduce you the practical algorithm to work with the distributional reinforcement learning. Okay, let's start. Markov decision process, just a brief recap and notation. Markov decision process is a 5-tuple state space, action space, reward function. On the slide, deterministic reward function, but it can be stochastic. So it can be distribution. And the transition probability map. And the discount factor, which is which allows us to measure the importance of difference between the current reward and the future reward. So to act in the environment, agent should follow some policy which maps some state to the distribution over possible actions. And following this policy, the agent goal is to maximize the return, the discounted reward, which is just sum of the subsequent rewards during the episode. Okay, this is the basic notion. Our goal is to maximize the expected return. Majority of the reinforcement learning algorithms are based on the concepts of value functions, which are the handy way to describe how good is our policy, if we allocate it in the, for example, given state. So, for example, state value function described the goodness of policy if we start from the state S, and then we will follow the policy. It's just the expected return conditional on state. And the second important function is the action value function, which is pretty similar. It's just the condition not only on state, but also on action. This function were already introduced by Sergey, but in the context of inference, so the only difference, in fact, is absence of Kyle divergence term. We don't need it because we don't have any prior here. So at each time step, we sample from the environment probability the subsequent state, and from the policy subsequent action, and get some reward. Okay, excuse me. Then, from the definition of the state value function, the the most important equation can be derived, the Bellman expectation equation. This equation is, in fact, it represents the connection between the value function in subsequent time steps. Specifically, we are in the state X and A, then we sample from the probability map the next state X prime, and from the policy the next action A prime. And with this equation, we can connect these values, these functions. The from this equation, we can derive the corresponding operator form, this one. And it should be noted that, in fact, this operator is described only in terms of the probability transition map and the reward function, and can act on any function which is defined on state action space. Okay. Formally, in this equation, we take an expectation over possible action which comes from the policy. But optimal policy will only consider only the best possible outcomes in the sense of expected reward. So the optimal policy will, in fact, maximize the expected return with respect to action. So if we are currently in some state, if we follow in the optimal policy, we will choose such action which lead to the maximum possible outcome in the future. So we are maximizing here. This is the only difference. And this is called Bellman optimality equation. And from this equation, accordingly, we can derive the operator form. And very important nuance is that this operator doesn't depend on any policy. It can act on function defined in state action space without any policy at all. Okay, so in reinforcement learning, Bellman expectation equation used to evaluate the policy. So repeatedly applying this operator eventually converges to the corresponding to policy pi state action value function Q. So we can start with some, okay, the question? The question was, what is R large without arguments? This is R large with arguments x and a. Yes, the first one. So this typo, this xa should be this, and this. Okay, the difference is, the question was, what is the difference between the equation form and the operator form? The difference is, I suppose, more conceptual. Equation is a strict restriction on which can be derived from the definition, but the operator form usually acts on some estimates, some approximation, so and or maybe even some functions which are not defined in this way. Did I answer your question? No? Okay, and let's try. This code xi is defined here, and it can't be nothing else. But the operator can act not only on functions defined in this way, but on, in fact, any function which defined in state action space. What? Quality by definition, you mean? Second line, yes, it's a good point. This should be, I suppose, definition, quality by definition. Okay, this operator repeatedly using this operator gives us a way to converge to the value function which corresponds to the policy, and this equation is in fact doing two things. First, it iteratively refine, just like this equation, iteratively refine our estimation of value function. And secondly, it iteratively improve our policy, because if we have some policy and corresponding value function, then if we act greedily in this way, then this policy acting greedily will be strictly better than the previous one. So this equation allows us to simultaneously refine and improve our policy. And on this fact, and Q-learning is based on this fact. Questions? No. Okay, Q-learning. So now we have Bellman optimality equation. So from the practical point of view, we have some current estimate, Q without hat. At the start, it will be some random guess. And from the Bellman optimality equation, we have the next improved version of it, refined and improved. Then at each time step, we just take weighted sum, and this is our next estimate. So specifically, we just get some sample, state, action, next state, reward, maybe from the different policy. Then computes our improved estimate, Q hat. Then with this equation, we update our Q and repeat this process. Why is it so important method? The answer is pretty simple. Under some condition, pretty simple conditions, theoretical guarantees on there are theoretical guarantees on the firstly convergence and secondly convergence to the optimal solution in deterministic MDP. Or to the deterministic optimal solution in MDP. Some questions, maybe? No? Okay. Okay, then let's turn to distributional RL. In distributional RL, distribution over returns plays central role. I remind you that on the previous slide we use Q, which is just mean of the value distribution Z, and all the equations were about the means of the distribution. In contrast, in distributional RL, the value distribution will replace the value function. So we will refer to the value distribution as a random variable Z.
Sorry, I have a question about the previous slide. I don't get how we update Q. We update policy, or we update what, and how is it done?
Okay. Formally speaking, we don't have any policy here. We just have Q value function, and at each time, and we can even not act. We just get some trajectory from the maybe different agent, from somewhere, but from this environment, and we use this sample to update our Q, our value function.
We do not learn our agent now, or we learn agent now. And if we learn agent now, how we do it? How the update is done?
How is done the update of the agent's policy?
Yes.
It is done in this way. In our agent policy is described only in terms of value function. in each time step of this algorithm, our policy is just acts greedily with respect to value function. So it is defined at each time step just implicitly by the value function. Okay, distributional Bellman operator. So now we work with distributions, and we can derive the similar equation, similar to the Bellman expectation equation, Bellman expectation operator, a similar distributional Bellman operator. And this equation should be considered as distributional equality. So this operator is designed in a way to consider only intrinsic randomness from the MDP. So which comes from the probability transition map and reward function. So it is not designed to estimate the uncertainty which comes from the maybe not so good parameterization or not so good estimation of that. Is it clear or not? Okay, who understands what I say? Oh, okay. Okay, let's suppose we estimate value function. We use some algorithm to estimate not value function, value distribution. So in this value distribution can consider two uncertainties. The first uncertainty, the true real one, the uncertainty from our MDP. For example, that in some state and action, the different reward may be given from our environment. This is the first one. And the second one, that we can have, for example, a bad estimation, a bad approximation, and this distribution, in theory, can handle this fact. But this equation is designed only for intrinsic randomness, not the parametric randomness. Who understand what I say? Okay, another one try. So,
come on, it's more or less simple. So our reward is actually a random variable. Up to now, we use the Q function, which was the expectation of this average reward. We start from the given state X and given action A. And now we're trying to work with the distribution directly. So since the average reward is a random variable, it has a distribution. And instead of working with the means, we're now trying to work with the distributions, right?
Yes.
And Z is a distribution, right? Or it's quantile.
Z is distribution.
Z is a distribution. So, and this is operator which converts the distribution into distribution.
Yes. Okay. So, what's happened here? How does this transform work? In fact, we just you should see that this function, it is the distribution, but x prime and a prime are variables too. So to apply the operator, we should get the we should get the state action pair. Then we should get all possible states and actions which could be in subsequent step. We should estimate the probabilities of each subsequent state action pair. And with these probabilities, we weight our distribution function in this pair, in these states and actions. we have a state and action, then we can after that we can get some different states, and we can do some different action in these states. So we have many possible outcomes of state action pairs subsequent, x prime, a prime. And in each those pairs, we have a distribution of reward. So in fact, this operator tells us just weights all this distribution sum with probabilities of these state action pairs and plus reward. So it should be an intuition, but okay. Oh, and squash with gamma, the distribution. Okay, and what? Okay.
I
Yes,
just
question?
want to ask, what is that null, the zero, I mean, at the start point? Or we don't have such?
Okay, if we use this equation to evaluate our policy, it can be any random guess, any distribution. So, I will remind this, is it not one distribution? This is a distribution on each pair of state action.
Okay.
It can be just random, and after repeatedly applying this operator, we will eventually converge to the right value distributions. But why, I will prove after on the following slides. Okay. We had value functions and had the colon, which were based on the value functions and on the Bellman equations. Now we have a value distributions and distributional Bellman operator. So firstly, why we should do that at all? There are some reasons for that. For example, the value function gives us only the expected future discounted reward. So this ignores completely the variance and the multimodality of the reward, which is given by the environment. Then, in case of co-learning, means equality doesn't mean, in fact, that we have right view on the distribution. So if we try to match distributions, we can have distinct distributions with equal means. So co-learning will be okay with that, but distributional not. But it's pretty clear that something is wrong with that. And the distributional operator can possibly establish a better optimization problem, and we will see that in experiments it's okay. The convergence may be faster, and the final policy may be better. So, of course, we would like to have the similar theoretical guarantees on distributional reinforcement learning as we have on co-learning. So, in case of co-learning, we have one of the key property of non-distributional Bellman operator, that it is a contraction in LP metric. So if we repeatedly apply non-distributional Bellman operator from the theorem of fixed point, we eventually converge to the unique fixed point. It's a very important thing. Who understand what I say here? Cool. So for non-distributional Bellman operator, the key feature is the contractivity, is that the operator is contraction. So from that we have convergence, we have unique fixed point, and we have optimality of fixed point. So that we will eventually converge to the optimal point, not some point. So can we derive similar results for distributional operator? It's the main question. It turns out that firstly we should establish some probability metric, because in the case of Q-learning we just measure the LP distance between the deterministic values, but in distributional reinforcement learning we should establish some probability metric between the distributions to talk about some convergence. Okay, Weierstein metric, I suppose it was defined already, but maybe I can show another view. Simple definition for Weierstein metric would be it is just the LP metric between the inverse CDFs, integral LP metric between the inverse CDF. It is one of the view on the Weierstein metric. So if we have some random variable u and y, the distance between the distribution would be just the integral between the inverse CDF, difference between the inverse CDF. So when the inverse CDF is defined as usual. Okay. Moreover, why Weierstein metric? Because it's a true probability metric, and it considers not only the difference between the probabilities of outcome, but it respects the distance between the outcomes. So by minimizing the Weierstein metric, we're not just minimizing the likelihood, like in KL divergence, but we also minimize the distance between the corresponding outcomes. Okay, in reinforcement learning, we will use the maximal form of this metric. So if we have two value distributions, we will just take each state action pair, then compute the distance, Weierstein distance, and then just get the maximum over all state action pairs. Is it clear? Is it clear to somebody? Okay, it's okay. So we establish probability metric between the probability distributions. Then we should clarify, so do we have some kind of convergence or not? So, we will use one Weierstein distance, which is just the integral of the module of the difference. So if we have two CDFs, it is just the area between them. Very simple. And so we can integrate for x, or for x, or for y, doesn't matter. Convergence. In the paper Distributional Perspective on Reinforcement Learning from 2070s, there was established a theorem, very important theorem, that the distributional Bellman operator is also a gamma contraction in the maximal form of one Weierstein metric. Just like the ordinal non-distributional Bellman operator is the contraction in LP norm. So for now, in theory, just in theory, it gives us all above nice properties: convergence, unique fixed point, and optimality in theory, just in theory. The question arises, but there is one problem. When we worked with the non-distributional Bellman operator, we operated with deterministic values of means of value, no, just value functions, just concrete numbers. And to parameterize them, we just take these numbers, and we don't need any approximations to represent one deterministic value. But in this case, we should somehow represent a distribution. And this fact necessarily comes with some approximations. And these approximations can break all these results. So, for example, we will apply operator, distributional Bellman operator, then we project onto some our parametric distribution, parametric family. And after that, it can be contraction, cannot be, it is this big question. So, to maintain all the nice properties which we have, which we want, we should construct the parameterization, the parametric family of the distribution in such a way that we maintain the gamma contraction. It's very important. So, how to define such good parameterization? It turns out that this parameterization was defined in 2072, and the main result was the suggested parameterization, the combination of the projection on the parametric family and Bellman operator is also a contraction. Who understands this statement? Okay, another try. We had Bellman operator, and in non-distributional case, we didn't need any approximation, so the contraction holds even in practical sense. But in distributional RL, we necessarily need some approximation, so this approximation can break the contractivity of the overall operator with the projection. So in 27th, were suggested such parameterization was proposed. And so after that, we have also unique fixed point from the contraction, also convergence, but the optimality is a question, and it is, as far as I know, is open question for now, because with some approximations, we necessarily converge not to a fixed point of just Bellman operator. Okay, we have fixed points of distributional Bellman operator. If we introduce some approximation, the composition of these two operators can have a different fixed point. It can have a different fixed point from the fixed point of just the Bellman operator. So the fixed point of the combination will not be optimal in the sense of distributions. It's a very important thing. Yes?
Not without parameterization, the optimality is some property of fixed point, yes? I mean, how do we get optimality for fixed point earlier?
I will repeat. How do we get the optimality of the fixed point in the co-learning in the table, no, in the non-distributional Bellman operator.
In distributional, but without parameterization.
Without approximations.
Yes. Is it some property of
it is point? The property of the form of Bellman equation. That if we will get if we will iteratively refine via the optimal form of the Bellman equation, we will eventually come to the optimal solution. It is a property of Bellman equation, I suppose.
Okay, thanks.
Okay, so we don't have, we doesn't necessarily have the optimality in the sense of distribution because we have different fixed points. But there is, I suppose, main open question. Do we have the optimality in the sense of means? Maybe even with approximations, we will eventually converge to the fixed point, to the optimal fixed point in the sense of means. Who understand what I say? It is very important. Okay, excellent. So I didn't find any proofs on that for now, so I suppose it is an open question. Okay. Then, so let's introduce parameterization. Our parameterization which doesn't break the contraction, the contractivity. Let's construct it in the following way. Let's fix some hyperparameter n, and after that we have our distribution as the sum of the uniform delta functions in the positions theta e. So we will have uniform equal delta function, but in different position. So our parametric family allows us just to move these n delta functions to better approximate our distribution. So in fact, it can be seen as quantiles of the approximated distribution.
So in other words, we try to approximate the distribution with a set of points, right?
Please repeat, I didn't hear.
We're trying to approximate the distribution with a set of points.
Yes.
In the space. And the only thing we can do is just to change the locations of these points.
Yes. More formally, not with the points, but with the Dirac delta functions.
Okay.
With the equal probabilities. It is an important fact. So, for example, if we have just one Dirac delta function, so we approximate the function with one delta function, with I suppose not one, but two delta function. Each represents 1/2 of the probability mass. Which point of the distribution which we should approximate would be very important for us if we talk about 1/2 of the probability mass. Somehow. I didn't hear. Median, of course. It's an excellent guess, and it is true. And I will later explain why. So we have such parameterization. So why it is a contraction? How? And another one question: how should we project onto this parameterization from the distributions, from some distribution? I guess it's time to break. No? Yes. Let's take a break, and you can think for a while. How can we construct? How can we project onto this parameterization? It's pretty easy. Okay, while people are coming, just a brief recap. We have contraction properties on non-distributional RL. We want which gives us good properties. So in distributional RL, we want these properties too. So we trying to, but we should approximate the distribution. So we're trying to construct our approximation in such a way that composition of Bellman distributional operator and projection operator will give us a projection, or will give us a contraction. So we are considering the following parameterization, which is just n delta functions and uniform delta functions. So we are allowed to we as a model are allowed to just move each of these Dirac delta functions. So we need to construct a projection. To do this, this is okay. To do this, we need to minimize the Wasserstein distance between the distribution and the approximate distribution in our parameterized family. In our family. So how to do this? The answer is pretty simple, and I will firstly show it on the picture. If we have n Dirac delta functions, the procedure is pretty simple. If we have some distribution, PDF, blue line, we should just split into n equal in terms of probability slices, and then we should place our Dirac delta functions into the median of each slice. This is just to show on the picture the result. Or in terms of oh, okay. Who understands this? Cool. Another one visualization in terms of CDFs. For example, we have this dark blue line. This is a CDF of the distribution which we want to project onto our parameterized family. So, firstly, we have hyperparameter n. We have n Dirac. Oh. Yes, n Dirac delta function 4. So, firstly, we split our distribution onto equal parts in terms of probability, 4 parts. Then, for each parts, tau 1, this is a right quantile of this split, of the first split. Then for each split, we should just take the median of the slice. So we split onto n parts. Then for each parts, we take the right and left quantile, and then we get the median of this split. So tau hat is our optimal parameterization. It will be our projection of the distribution onto our family parameterized. So okay, this is a non-formal description. This fact, this procedure comes from this fact. If we have some distribution, some CDF-F, and we will try, and we will have some, and we have some parameterization theta. So if we integrate from tau to from one tau to another, then the one Wasserstein distance, the minimization of one Wasserstein distance is given by the half sum of the quantiles. This fact comes from the this. If we have just ordinary regression problem, and if we use L1 loss, the solution would be the median of the variable. Right from this fact implies that the minimization is half sum of the quantiles. And from this fact implies the construction of the projection. This is not full formal proof, just a sketch. Okay. So, for now, we have some parameterization. We have a way, we define, we understand, now we understand how to project from the distribution to the parameterization, but the problem is our distribution, we don't know the distribution. Because I remind you that this is the distribution of the rewards, so we just get some samples from it. And we somehow should estimate quantiles of this distribution from the samples. Fortunately, there is a pretty old technique for this, which is called quantile regression. We have quantile loss function. Here it is. This is it penalizes. Oh, this is a typo. This should be 1 minus tau. This should be tau. So we penalize overestimation by tau and underestimation by 1 minus tau. So it is just, in fact, L1 loss with a bit differently rotated lines. This, if we will minimize this loss, so we have sample Z, we have the current estimate theta of quantile. So the difference is penalized on tau if we overestimate it, and penalized by 1 minus tau if we underestimate it. So it naturally comes. The solution is pretty simple. We will get in expectation we will get a quantile, just like. If tau is equal to 0.5, we will get the median. It will be just L1 loss. And if we rotate a little bit, we will get different quantiles of the distribution. This loss will give us, to be precisely, the gradient will eventually, the gradient is unbiased. We will get, if we use this loss, we will get unbiased estimate of gradient, which eventually will converge to the quantile. And we theoretically understand how to project our distribution on the parametric family. Then we derive a practical solution in the sense that we don't have a distribution, but we have samples. So this procedure gives us a way to estimate the quantiles of the distribution. which straightforwardly gives us the parameterization. So, okay. Here we comes to, at this point, we have theoretical guarantees on the convergence and the uniqueness and the existence and uniqueness of the fixed point. But we don't have any guarantees on the optimality of the solution. Okay, let's proceed to the practical algorithm. It's pretty simple. We establish some. Okay. In fact, in practical algorithm, they didn't use exactly this loss function because it hasn't gradient and 0, so they relaxed it a bit and use Huber quantile loss function, which is just a symmetric quadratic function at some at 0 and some near 0, and ordinal quantile loss function in other points. So and we come up with the first hyperparameter, which is the number of delta functions, and the second, which is the parameter of Huber loss. Then algorithm. We get some sample from some policy, which consists of state, action, reward, and next state. Then, for now, we have here we have in the case of co-learning, when we apply neural networks, we usually just have state as input to our network, target network, which predict mean reward for each action, just a state value function. In the case of quantile regression, reinforcement learning, we have a network which input is x and which output is the number of actions multiplied by n. So for each state action pair, we have n quantiles. Thus, to get the state value function, which is the mean of the distribution, we should just get the weighted sum. Then, just like in co-learning, we greedily take the optimal action with respect to co-values, state action values, and we use Bellman operator to get the improved estimation of each quantile. And the important thing to note is that we have the initial prediction data, n quantiles. We have the consequent prediction, not consequent, improved prediction tau theta g, which is n quantiles too, in fact. And then, using the sample R, we update each theta e just like if we have n samples, because we consider our reward, our sample of reward, as n samples using n quantiles. So we just get quantile, each quantile, adding this reward, and eventually, we get n. We consider these n values as samples, as n samples. This is not so correct. Maybe not so correct way to compute, but maybe formally this is right. But there are some questions, but I think we will discuss it on the seminar with Arseny. So, for each quantile I, we have n samples, and we then compute our loss with respect to I, with respect to j, and then just optimize this loss with respect to parameters of this model, theta from state and action. Are there any questions on this algorithm? Yes.
Okay, a set of questions. Theta. What is theta g? It's the set of points with Dirac functions.
Yes.
And why do we need some optimization if we have if both q on x and a and q on x prime a prime are both sum of n Dirac functions with just moved points?
Can you please repeat the question?
I mean, when we looking for percentiles, we're looking for percentiles for this specific function, sum of Dirac functions.
We
yes?
have an estimate of quantiles of value distribution, theta. Estimate of quantiles of value distribution, yes. And?
But isn't...
But
couldn't we find it analytical? I mean, if the function is just the sum of n Dirac functions, then its percentiles are
okay.
mix of this.
The question was, why can't we just analytically compute these quantiles?
Yes.
The problem is the following. In the ordinal co-learning, we don't even know until convergence even the means. We are trying to learn means. The problem is we have just several samples, and the second that these samples are constantly coming from different distributions. Because we change our policy, the distribution of rewards are changing, and we get some samples, so this is not a straightforward problem to solve analytically. Just like this is akin to we can't just compute the mean in co-learning just from the start. This is just this exact problem. Any other questions? Okay, there are some words about that. This quantile regression performs better than the first proposed algorithm and better than deep Q networks. But the recent results shows us that this is not so simple, and the previous one method, even having the theory practice gap, from time to time performs considerably better than quantile regression reinforcement learning. So, for example, you can obtain the results when we will have monotonically increasing rewards, and at some time something fail, and you will lose all learned policy, all the results. So this algorithm just fails. There are it's an open question how to choose a distributional reinforcement learning algorithm to fit your concrete problem, because it can fail. Thank you. This is the end. Thank you for your attention. And I suppose we will have a break and then the seminar. Arseny?
Please be sure that you download a new version of seminar before the seminar, not just after the beginning of the seminar. Please update it. Sorry? How new? Something like 2 hours ago. So it's on GitHub, on our GitHub. Please download it before the seminar. There are several versions. It will be collab versions and the local versions. I personally do recommend you to use local version of the seminar because of the pure internet here. So I think that it will be better.